A great white shark leaves a crowded seal colony, and you might expect it to follow prey along the nearest coast. Instead, its tag records a direct journey into open water where no obvious feeding ground appears at the surface. Weeks later, the animal begins repeated dives through hundreds of meters, rising and falling across deep blue space. Another shark remains coastal, while a third eventually returns near the place where it was tagged. These tracks transformed the great white from a shoreline ambusher into a far-ranging ocean traveler. They also replaced one simple mystery with several harder questions about destination, timing, and purpose. Great white sharks, Carcharodon carcharias, migrate across regional systems that differ greatly around the world. No single route describes every population, sex, age class, or individual. Some movements follow rich coastal feeding areas, while others cross entire ocean basins. Offshore tracks can converge within broad regions that look almost empty on ordinary maps. At depth, diving patterns change, suggesting new behavior without revealing exactly what the sharks encounter. Satellite tags report positions and environmental histories, but they rarely show prey, mating, or social interaction directly. The resulting map is evidence of movement, not automatic proof of motive. Surprise survives because the strongest observations expose important behaviors while leaving their functions partly hidden. To investigate, the shark's route must remain connected to the limits of every instrument recording it. Great whites inhabit temperate and some subtropical waters across multiple ocean regions. Adults are capable predators of seals and sea lions, but their diet is broader and changes with age. Younger sharks commonly consume fishes and rays before large marine mammals become important prey. Coastal aggregation sites make sharks visible because predictable prey or seasonal conditions concentrate them. These sites once encouraged the mistaken impression that the animals belonged mainly to local shorelines. Individual identification later showed that some sharks return to particular regions across multiple years. Photo records use natural markings, while electronic tags reveal movements occurring between sightings. Pop-up satellite archival tags record depth, temperature, and light, while attached to a free-swimming shark. After release, a tag floats upward and transmits summarized information through satellites. Light-based longitude estimates are less precise than modern satellite positions obtained at the surface. Sharks do not always surface long enough for a transmitting tag to acquire an accurate location. Track reconstructions, therefore, contain uncertainty, especially across long periods beneath rough water. Acoustic tags offer precise detections near fixed receivers, but remain silent outside the listening network. Combining methods improves coverage without removing every spatial gap. These measurements established large migrations by sharks from northeastern Pacific coastal aggregations. Some travel between the North American coast and waters far offshore before returning seasonally. Researchers informally called part of that offshore region the White Shark Cafe. The name describes a recurring destination, not verified evidence that sharks are eating there. Comparable long-distance movements occur elsewhere, including routes connected with southern Africa and Australia. Regional paths differ because prey fields, currents, breeding opportunities, and geography also differ. Female and male schedules can diverge, but patterns are not uniform across all populations. Some mature females may be absent from aggregation sites longer than males. Pregnancy and reproduction are plausible influences, though birth locations remain poorly documented. When you inspect an offshore record, the first surprise is often how purposeful the horizontal transit appears. A shark may hold a relatively steady direction across water, lacking visible landmarks. Geomagnetic information, odors, currents, temperature structure, and learned spatial memory are all candidate navigation cues. Laboratory and field research supports magnetic sensitivity in sharks broadly, but exact great white navigation mechanisms remain unresolved. A straight reconstructed line also hides smaller movements when location estimates are sparse. Navigation hypotheses must predict responses to manipulated cues before they can explain an entire migration. The second surprise comes when horizontal travel turns into repeated vertical movement. Tags record rapid ascents and descents that can continue for extended periods offshore. Scientists sometimes call persistent oscillation bounce diving, a description rather than a functional explanation. The pattern may relate to searching for prey distributed by depth, may also help sample temperature, odor, or magnetic information across water layers. Social or reproductive functions have been proposed for some offshore behavior. None of these possibilities is proven solely by a jagged depth trace. If the tag records temperature changes with depth, it can reveal repeated crossings of ocean layers. Acceleration sensors add fine movement, potentially separating steady glides from bursts associated with pursuit. Even then, a burst does not confirm that prey was captured. Animal-borne cameras can provide direct scenes, but attachment duration and field of view remain limited. Biochemical evidence from tissues integrates diet over time without identifying every feeding location. The third surprise is return fidelity after months beyond coastal observation. Some individuals reappear near previous aggregation sites with remarkable seasonal regularity. That return suggests persistent navigation and memory, though routes may shift between years. A seal colony offers concentrated energy, making repeated use evolutionarily understandable. Yet not every returning shark arrives on the same date or remains for the same duration. Ocean conditions alter prey availability, temperature fronts, and travel costs. Individual size, sex, reproductive state, and prior experience may change the decision to remain or depart. The migration is therefore a flexible schedule built around recurring opportunities rather than a fixed railway. For the shark, a moving prey cue can trigger acceleration, approach, and an ambush from below. Successful capture provides a large energy return that can help finance later travel. When prey density falls, continued searching may cost more than departure toward another opportunity. Offshore, a deep scattering layer can bring fishes and squid upward at night. Sharks crossing such layers could forage, but overlap alone does not prove consumption. Repeated depth changes might increase encounter probability with vertically migrating prey. Consequence could be energy gain, environmental sampling, or both, and direct evidence remains scarce. You must therefore resist, turning every migration waypoint into a confirmed feeding station. Great white movements matter beyond curiosity because these predators connect distant ecosystems. A shark can consume prey in one region and later transport nutrients across broad distances. Its presence can influence prey behavior, though ecosystem effects depend on local density and context. Migration also carries sharks across national jurisdictions with different protections and fishing pressures. Animal protected near one aggregation may encounter hooks, nets, or vessel traffic elsewhere. Conservation based only on famous coastal sites leaves the connecting corridors poorly represented. Reliable population estimates are difficult because wide-ranging individuals can be counted inconsistently. Separating regional populations requires genetic evidence alongside movement records. Some groups exchange individuals, while others show enough isolation to demand separate management. Climate change may shift prey distributions and thermal habitats, altering routes without immediately changing shark abundance. The same tag technology revealing migration can establish baselines for detecting those future changes. Important unknowns remain concentrated around mating, pregnancy, birth, and the survival of newborn sharks. Directly observed mating in the wild is exceptionally rare, so scars and co-occurrence provide incomplete clues. Nursery areas are inferred from repeated presence of young sharks, not assumed from a single sighting. Future multi-year tags must last long enough to connect coastal departure, offshore behavior, and reproductive events. Younger sharks need better coverage because their routes may differ from those of conspicuous large adults. High-resolution accelerometers paired with cameras could validate which motion patterns represent feeding. Environmental DNA might confirm nearby prey communities, but it cannot prove what one shark consumed. Stable biochemical markers can test whether offshore feeding contributes substantially to the shark's tissues. Expanded receiver networks could resolve coastal corridors, while international data sharing closes jurisdictional gaps. Genetic parentage work may identify reproductive connections without witnessing mating or birth. Models should retain uncertainty instead of drawing smooth certainty through months of missing positions. The strongest future evidence would join location, behavior, prey encounter, and reproductive state in the same individual. Until that happens, each instrument illuminates only one layer of a migration performed beyond ordinary sight. The shark that left the seal colony may return, cross an ocean, or adopt a route not yet recorded. Its tag can show where and how deep, while purpose often remains divided among competing explanations. You can follow the line across a map, but the decisive encounters still occur inside an immense three-dimensional habitat. Great white migration is verified on astonishing scales, yet its offshore dives, reproductive routes, and navigational cues remain scientifically open.